Okay, and we're recording. So last time, just a quick reminder, we were talking about Gauss's divergence theorem, and recall it follows a pattern, right? It's the same pattern that we used for Green's theorem. It's the same pattern that we used for the 2D divergence theorem. It's the same pattern that we used for the fundamental theorem of line integrals, frankly. It's a pattern we've seen several times before. But just as a reminder, we viewed flux. And keep in mind, in this context, when I say flux, I mean boundary flux. We're talking about Gauss's divergence theorem. Flux always means boundary flux. Flux is a quantity of interest that we defined clearly once we actually finally got around to defining what we mean by the boundary of a three-dimensional solid. In particular, the missing component there was orientation, right? So we had to have a standard convention of what orientation does that boundary have, and of course the rule is it goes away from where the solid is, typically outward, but unless you have an air bubble inside of your solid, then everything's different. Okay. All right. So that's the quantity of interest. Second thing to note is that it is an accumulating quantity. And this is a matter of drawing pictures and noticing how the orientations on shared faces always go the opposite directions. And that's what makes it all work. In some sense, this is really, this is kind of the kernel, this is the nugget that is underneath it all. That is why it works. Then lastly, there was a notion of density that we made sense out of. If you have an accumulating quantity, you can talk about stuff happening in the interior, even though it's measured on the boundary. And once you know where it is, you can talk about how much per unit volume. And that density, I didn't derive the formula, and that's details that are less important than the background of where does it come from, how do I interpret it, but the result, what the density is, flux per unit volume is divergence. Okay, so that's where the divergence theorem comes. Well, let's see. This is my preferred way of thinking. I'll say about how to think about the divergence theorem. And then we did an example, and I believe that's about where we ran out of time last time. So I'm not going to go through this example again. I do want to hit one highlight, though, that I think is particularly important. There's plenty of other important details in here. But the one that I'm going to take an extra moment on is don't forget about the orientations. The orientations are really important. So our surface was given as an circled the wrong thing, inward-oriented unit sphere. And so our surface is this. Is that a boundary? Sadly, no. Right, it's not oriented the correct way to be a boundary. This is not a boundary. You cannot apply Gauss's theorem. What you can do, though, is say that it's off purely by a minus sign from this other surface called S minus. And S minus is a boundary, and to S minus, therefore, you can apply the divergence theorem. Okay, all right, so a lot of other important details to keep in mind. We did this last time. Okay, so picking up from there, we're going to talk about some physics examples today. We're going to spend a lot of time on these physics examples. There's a lot to say. This is for kind of intuition purposes. I suppose you could say one partial purpose of what we're doing here is to see how math can be used to apply to physics problems. But to be totally honest, that's not my primary motivation. My primary motivation is kind of the opposite. My primary motivation is that I'm going to take things that we hopefully have some sort of intuition for already and then show what the divergence theorem looks like and therefore how you can reasonably interpret it in these contexts where we already have some intuition for what's really going on. And said differently then, my goal here is to use our existing physics intuition to help us understand the math. So this is not math in service of physics. This is physics in service of math. And I think this is a nice thing. So my first example was about light bulbs. Y'all know how light bulbs work? I mean, pretty much, right? There's a hot spot in the middle. And it used to be like a filament back in the incandescent days, and now it's an LED. But it remains that there is a teeny tiny little hot spot where all the photons come out of, right? And then everything else is just, kind of minor, relatively minor, keep it clean, kind of, keep the dust out of there, kind of stuff. Mostly the LED is what does the work. Okay, and so these LEDs, they generate photons, right? And I hope everybody's familiar with this fact of physics. Light is communicated by little particles called photons. Okay. And now they are particles and they are discrete, but I claim that they flow like a fluid, and I'll remind you that in fact all fluids are made up of particles, right? Water seems like a continuous substance, but if you get down to the atomic level, it's a bunch of little tiny particles, molecules, I guess. So photons emitted out of a single point source flows like a fluid. Okay, so the couple things to say about this fluid. Unlike most fluids, the fluid gets generated. All right, we don't have that with water. Water doesn't generate. I suppose rare circumstance you could dream up a condenser in a distillation situation, something like that, right? But most of the time, when you're looking at fluid flows of water, there's no water being generated. Here, the fluid is being generated. Here's the other thing that's a little weird about this. Well, anyway, noteworthy, perhaps. But the fluid density doesn't change with time. The fluid density is constant as far as time is concerned. So what I mean by that is, if you look at a light bulb, there's a ton of photons being generated, but it's not like those photons are coming over here and then in this region of space they're kind of collecting and you're getting more and more and more photons in this one little region. No, of course not. Photons come in, they go out, right? And it keeps shooting them out and they just keep on going, right? And so we have a steady state situation that the amount of photons is, in any given region at any given time, amount of photons is pretty much constant. Right? Does that make sense to everybody? Okay. All right. Okay, so the particulars of this fluid. One other thing I need to say, and I need to append to the notes here. When we say that we're going to represent this flow with a vector field, don't forget we're using density times velocity to represent the flow of the fluid. And you can even actually see that in the diagram. You'll notice perhaps that the field line that I've drawn there, the field vector that I've drawn there and the field vector that I've drawn here are conspicuously different magnitudes. Does this mean that the photons are slowing down as they go in this direction? Of course not. Right? Speed of light's a constant. So it's not a velocity thing. It's a density thing. As the photons get further away from the origin, right? Any number of photons emitted in a given period, well, they're all close together when they first get emitted, and as time passes, well, they spread out, right? And so the photons are spread out further away from each other the further you get away from the source than they are when you're right up next to the source. Right? So that's why when you shine a flashlight, at a nearby wall, it's very bright, but if you shine it, across the quad over there to the other building, it's nowhere near as bright. All right. That makes sense to everybody. And then the particulars of this vector field, are that this is inverse square radial. As it turns out. And if you're curious why that might be, feel free to come talk to me. I'd be happy to show you. Nothing to it. But anyway, that's what it is. Okay. How are we doing so far? Everybody on board? Willing to buy it? Okay. All right. So what I'd like to do now is talk through a couple of scenarios. I'm going to compute divergence in a few places. Let me remind you where divergence comes from. Divergence is flux density, right? It's literally flux per unit volume. And so that's the way I'm going to compute divergence here. I'm going to actually talk through various surfaces, boundary surfaces, that is, and ask, well, how much flux is there through this surface? And how much volume is inside of this surface? And argue from that. So here we go. Let's start with a little surface around the bulb itself, around the LED, the actual light source itself. Okay, so what's the value of the divergence there? Well, first of all, what's the flux? How much flux of this photon fluid flow is there through this surface? Well, here's the thing. When this LED creates photons, right, it generates photons, how many of them pass through this blue surface? All of them. 100%. Right? They all pass through this blue surface. They got to get out, right? They're starting out inside the surface. They got to get out. That means they pass through. Simple as that. That makes sense to everybody? So there's however many lumens this light bulb is. If this is a 1500 lumen light bulb, then 1500 lumens of flux goes through that surface. Okay. All right, but now keep in mind, that's flux. What is divergence? Divergence is flux per unit volume. So let's talk about how much volume is there inside of this. Oh, whoopsie, what happened there? How much volume is there inside of that little small surface? And keep in mind, those LEDs are pretty small, right? They're teeny tiny. And so I can make this surface as small as I want. I'm going to just make it just barely big enough to contain the whole LED. And that's pretty small. That's a very low volume. So what we have is 1,500 lumens of flux divided by a very small amount of volume. And that's large divided by small, and that's massive. Right? So at this point, where the LED is, the divergence is very large. Everybody buying it? Okay. All right. Now, next question, though. Let's see here. I'm just going to do this. I'm going to say it's same deal. Let's look over there. Let's look at this point there, and let's talk divergence. How would I compute the divergence? Again, I'm going to do flux per unit volume. And let's start off with the question of flux. So, looking at this surface, what's the flux through that surface? Keep in mind the photons are flowing like this, right? Coming out of the LED. Keep in mind further that we have an orientation. Oh, whoops, and that needs to be blue. We have an orientation on this surface. And so when we say flux, boundary flux, I mean with the understanding that this is the orientation. So here's the thing. When the photon first encounters this surface, look at what's the deal with the orientations. It's going inward through that surface. The proper orientation is outward. That means that when the photon first goes in, it counts as negative flux. Then it travels through the interior a little ways, and then eventually gets out here to the outer edge, and when it leaves, it is going outward, as it should be in some sense. In other words, in the positive direction. So, weirdly, what that means is every photon counts negative and positive. Said differently, there's just as much flux inward as there is outward. Said differently, the grand total flux is 0. What do you think about that? Does that make sense to everybody? Everybody's happy. So if the flux is 0, then when I divide by the volume, however small, who cares? It's 0 divided by small, still 0. And so over here in this general area, let's see here. I should color code this more carefully. Let's do it like this. When we are at the center, the divergence is very large. When we are anywhere else, anywhere other than where the LED actually is, the divergence is 0. Okay. Now, I haven't really gotten to the punchline yet, but so far, is everybody on board? Is everybody buying it? Yeah.
If you were looking at a boundary that wasn't a circle, then wouldn't you have something where, like, you have a photon go in at a different angle relative to the surface that it comes out?
The dot product with the normal vector kind of takes care of all that in some sense. So keep in mind, I mean, the formula for flux is really just a tool for computing what, if you think about it, I mean, let's take it back to the fundamentals of what flux really is. It's quantity of fluid, right? Quantity of fluid passing through the surface, accounting for orientations. So don't think in terms of angles, think in terms of quantity of fluid. And if in some region, and let's take, in this green region that I have over here, we agree that the photons aren't collecting. And so if they're not collecting, and that means that the amount of photons that are in that region is always the same, then the number of photons going in at whatever angle, right? The quantity of fluid going in and the quantity of fluid going out, it's got to be the same. Otherwise, we'd be collecting photons. Does that make sense? Yeah. And if you look at the dot product formula for flux and actually compute the vector surface integral, which would be pain, right? But if you did it, you get 0, still 0 for this intuition. Taking it back to first principles reason. Yeah, great question. Anybody else? Okay. All right. Okay, so what's the point of this exercise? So let me remind you that I keep making the case that even though certain things are measured and we think of them as actually being on the boundary, such as let's take this change here. That change is computed by looking at these 2 points, A and B. We look at the value of the function there and the value of the function there. And that change happens, it's measured anyway. I should say it's measured on the boundary. But is that where the change actually happened? I don't know. Of course not. It's perfectly obvious. Change happens in the interior. You can see the change happening right there for these values of x. Right? And I've made that point. In this context, I think it comes through pretty clear. But then I make similar statements about circulation. And I make these much harder to relate to suggestions that even though we measure circulation on the boundary here, I claim that it's actually happening in here in the interior, and there's a certain amount of hand waving involved there, and it seems kind of, well, I guess you could, if you really want to see it, you could maybe persuade yourself, but it doesn't seem like you should have to view it that way. Right? So one of the things I really like about this example here is that it really brings it home. That divergence points to where change is happening. And so let's talk about the flux that happens, the flux that's measured through this purple boundary. Right? And there's, of course, there's 1,500 lumens, right? This is a 1,500 lumen bulb. How many lumens worth of photons are passing through this purple surface? Well, all of them, right? All the photons have to exit the bulb. 1,500 lumens. And then I ask, okay, well, where did that actually happen? Did the flux actually come from the boundary where I'm detecting it, where I'm measuring it? And well, of course not. It comes from where the LED bulb is, right? And what's beautiful is divergence is actually pointing us to that, right? The fact that the divergence is massive, where the bulb is, that's the divergence telling you. In the same way that derivative, being large here is telling you that change happens here in the interior, where you can see the change happening, right? The derivative tells it to you here. Divergence tells it to you here. The photons that you're seeing on the boundary, they're coming from where the divergence is huge. And how much of this flux that I'm measuring on the boundary, how much of it comes from this green zone over here where there's nothing, where it's just vacuum? Are there any photons coming from there? No, of course not. Divergence is 0, basically telling you there. Yeah, there's nothing coming from there. Does that make sense to everybody? So this is what I like to think of as a physical, you can see divergence happening. The light bulb is, the LED is the divergence. Right? That's how bright is, that's how hot of a hot spot is that LED. Okay. All right. So, for your consideration. Alrighty, next example. Now, here we're going to see a different kind of a fluid. I want to talk about a gas, and I call this evacuation of a gas. By that, all I mean is we have a certain amount of a gas. Maybe think of it like it's a nebula or something out in space, it's a certain amount of gas there. And then let's suppose that the gas just starts expanding. Right, so maybe the temperature increases, and when you increase temperature, then volume increases, and that means that the gas expands. That means that the particles of gas are going to start moving outward, something along these lines here. What do you think? Is that plausible scenario? By the way, I claim that if you did have like a nebula of gas, and if you were to start raising the temperature, that this is approximately what that vector field, movement of the gas would look like. And the reason why is, in some sense, wherever you are, right, how far you are away from the center tells you how much, if you will, how much of the gas, by it expanding, is going to be pushing this point further along. Right? So this point here, there's a lot of gas between it and the center, and if everything if all the, every little pocket of gas is getting bigger, there's a bunch of little pockets of gas along in there that, by them getting bigger, pushes everything outside of it faster outward. So this is being pushed by a lot of gas, whereas by comparison, if I were to look at this dark blue spot right there, right, well, that's only being pushed by, there's a much smaller little collection of a little bit of gas that's pushing it further along, but not very much. So the further it is away, the faster it's going to be moving in the expansion. So this is actually pretty plausible. What do you think? Willing to buy it? Okay. All right. So here's the thing. Now this is a different kind of a fluid. Let's come back up here to this story here for a second. And reminder, the photons are being generated out of nothing. Right? They're the photons that are being shot out of our light bulbs here right now. It's not like the light bulb has a supply of photons that it's throwing. Right? It's generating photons by some, cool physics. Right? That is not what's happening here. There is a flow of fluids, but it's not because gas is getting created, right? No gas, no fluid is being created or destroyed here. It's just moving. Okay. The other big difference to note, coming back up here to to the light bulb story. This was a steady state thing, right? And we talked about this. The photon density doesn't change over time. With the light bulbs sitting there where they are, if I look at, how many photons are there in any given little region of space? Well, there'll be some. From the bulb over there's more coming in, the exact same number going out, and altogether, in any given little fixed region of space, the number of photons is not changing. Right? We're not collecting photons. And we're also not burning or losing photons. No photons are disappearing, right? In any given region of space, the number of photons is just constant. Okay. So that also, not so here. Here, density is changing. Right, I've got a certain amount of gas, That's it. There's a finite amount of gas, and as it expands, that means that there's less and less gas per unit volume that remains in there. Right? This is also just a kind of a physics thing. If you remember your whose law is it? Hooke's law? No, that's Springs. What's the one with is it the ideal gas law? Is that what they call it? Doesn't it have a name? Is it just ideal gas law? I can't remember the name if there's a name. It doesn't matter. Sorry? Or is it ideal gas law? Okay. Anyway, so one way to say it is that as temperature goes up, volume goes up. Another way to say it is that as temperature goes up, density goes down. Right? Because it becomes less dense because the volume is expanding. So, again, inconsistent with the previous example. Here, density does change with time. Not with photons, but yes, with gases. Okay. All right. So different kind of fluid flow situation. All right. So let's write down the divergence theorem, try to make some sense out of it. Here you go. There's the divergence theorem. Let's think about the left-hand side here. Flux. Right? It's measured there on the boundary of the solid. And it's just, very simply, it's a measurement of how much gas is leaving through the boundary there, through the boundary of the solid. Is that cool? Okay, now on the other hand, we can compute the divergence, and this is an easy calculation. I'm going to leave that for y'all to do. It's a good little exercise. Don't forget we have a formula there for our vector field. You know the formula for computing divergence, and just punch it on out. Ends up being this value 3K, which you'll notice doesn't depend on X, Y, or Z. This is a constant, right? And so what is it then that this divergence is really telling us here? And I claim that it's telling us, in some reasonable sense, where this flux is coming from. Right? This flux that we see on this boundary that represents there being less gas, less fluid on the inside of this sphere. This divergence is telling us where it's actually coming from. Now, if you want to be rigid about it, you could make the case that, the gas that's leaving, where does it come from? Well, it comes from right next to the edge, and that's, it was already close, and that's why it got pushed out. Okay, true. But if you think of it as, look, the reason this gas got pushed out is because of things that happened closer in. There was expansion that happened on the inside that pushed it out, right? In other words, where is there less gas as a result of gas leaving through the boundary? Where's that gas deficiency going to be? If gas is leaving, then as a result there's going to have to be less gas in the interior. Where in the interior are we getting less gas? The answer is everywhere. Right? This being a constant, right, tells us that the density is decreasing at the same rate everywhere in the interior, which we already talked about, right? If we're raising the temperature at a constant rate, then it all expands sort of uniformly. And effectively, even though the flux is measured on the boundary, this flux is a manifestation of density decreasing everywhere throughout the interior. And again, divergence points to that for us. Does that make sense to everybody? Okay. All right. So we've got two examples now of interpreting fluid flows with the divergence theorem, and again, they are different. These are different kinds of fluids. In the first one, fluid is being generated. By contrast, in the second one, there's no fluid being generated. We have a fixed amount of fluid. So, different. Secondly, density is constant in our first example. Not so in our second example. In our second example, density is changing. Right, so they're fundamentally different kinds of fluid. So the next point I want to make when we get to the next page here is that not every fluid is going to be strictly one or the other of these things. You could have a fluid, and by the way, we're not going to do any examples of what I'm talking about here. This is just kind of foreshadowing for, if you take a fluid dynamics class at some point in the future, or, whatever. Some other context, you might see some of these ideas. And you might have both. And here's the way I like to think about it. I think this is a natural and relatable way to think about this. That there really are two things that can happen when you're generating fluid. Now let's just imagine that we've got some scenario, some solid with a boundary surface, and the fluid is being generated by some amount, whatever that amount is. Don't worry about what that amount is for the moment, but whatever that amount is. And I claim there's only two things that can happen. When you generate fluid on the inside, one possibility is it could stay, in which case the quantity of fluid is going to increase. In other words, that generation rate, however much fluid is, whatever the quantity per unit time of fluid is being created, if it stays in your region, then that's going to be visible in the derivative of the quantity. Right? Okay, here's the other possibility though. When you generate fluid, it might not stay, it might exit your region. If it exits your region, it has to pass through the boundary of your region, right? Exiting means passing through the boundary, and that means flux, which of course is also a rate. It's, quantity per unit time. Right? So this is the way I like to think about it. When you generate fluid, it either stays and contributes to increasing the supply, or it doesn't stay and its exit is part of the flux. So in our first example with the light bulb, that term was 0. Right? There was no changing density. Right? There was no changing density at all. Right, and so said differently, flux related to how much the fluid was being generated. That was the light bulb example. Excuse me. In the second example, the generation rate was 0. Right. In the second example, this is the gas example. There wasn't any fluid being created, or there wasn't any fluid being destroyed. It was a fixed amount of fluid. And so flux relates to how fast the total quantity of fluid is changing. Right? So both of the cases that we saw on the previous page are special cases of this more general thing. And in some general scenario, you might have to decide, well, wait a minute, let's look at your physical situation and ask, well, is it one or the other of these, or is it some combination? But this rule is always going to hold. Okay. As this relates to divergence, we're just going to take this equation and pretty much just divide by volume. Right? Consider differential pieces of quantity and divide by volume. Flux per unit volume, divergence. Mass per unit volume, density. Right? And then, all right, and this is one that I don't know what to. This is not going to be particularly relatable. I mean, we don't have a previous understanding of generation rate. But if you were to imagine that, the fluid in question was maybe being created all throughout the solid, perhaps. I mean, maybe you have a glowing, instead of a glowing light bulb at a single point in the interior, maybe you have a gas that's like a neon gas, and all of the gas is glowing, and so the flow of photons is being generated by points all throughout the interior, right? Then you could ask, okay, well then how much of that per unit volume? And I'm just going to give that a name and call it generation rate density. But anyway, that's not something we can relate to from past experience. Okay. All right. Okay, so like I say, this is all kind of foreshadowing for future courses or other contexts where you might need divergence. And so, keep in mind that it can be more complicated than the previous examples. Okay. All right. So next example, I want to talk about gravitational fields. I like gravitational fields because they're relatable. They're more relatable than electric fields in some sense. I mean, we've been well aware of gravity for much longer than we've been aware of electricity. I think it's a fair statement, right? And you can see matter. You can see mass. You can't see gravitational fields, but you still have a visceral kind of we've been dropping stuff and having it splat on the floor since we were kids, right? So the idea of gravity goes down, and this is a more relatable thing than electric fields, and certainly way more relatable than magnetic fields, right? So I'm going to call this a fairly relatable, example. Here's the rule. We've talked about this one before. For a single point mass, and just a real quick reminder, it's not really physically, there isn't really such a thing as a single point mass. But this is a useful way to kind of get our foot in the door to talk about gravitational fields. Just consider just one particle of mass, and it'll generalize in other ways. So anyway, for a point mass, here's the gravitational field. Again, we talked about this back in Chapter 3. And I'll remind you that you can rewrite that like this, which means that it's radial because it points directly out from the center, and furthermore, it is inverse square. Right? So this too is inverse square radial. Gravity is inverse square radial, just like the fluid flow of photons coming out of a light bulb, also inverse square radial. And this is what I like to call an eyebrow raiser. Right? What are the odds? How about that? That's weird. The flow of light out of a light source and the gravity created by a point look exactly the same mathematically. One big difference, this is just a constant, nothing to worry about, but of course, this being gravity being down, this constant's negative. And by the way, you'll notice I drew these arrows, again, outward. Gravity, of course, thankfully, is downward. Would be a weird physical universe if gravity was repulsive, right? I don't even know what would happen there. But anyway, so that is one big difference, but that's a physical difference. Right? That's not mathematically. It's just a constant. Who cares? Constants don't do hardly anything. Right? So, like I say, eyebrow raiser. That what are the odds that gravity behaves as if it's communicated by emitted particles? Because the direction and the magnitude of the gravitational field is exactly as if it were created by little particles that fly out of matter in the same way that photons fly out of light bulbs. So here's the thing. When something that coincidental happens, it makes people think, I wonder if this is actually what really is happening. Maybe that's how gravity really works. Right? And I don't know how much y'all are familiar with how much, historically physicists have been uncomfortable with the idea of what they call action at a distance. Right? I mean, if I have a friend standing next to me, if I shove him, then he falls over. Why did he fall over? Well, because I made contact with him. I physically touched him and pushed him. That's why he moved. That's action by contact. That's not hard to relate to, right? But action at a distance, that I'm just right here, and then, some guy in the back just falls over, like I got the force or something, right? I've been watching Andor recently. So that would be weird, right? That's creepy. So this idea that gravity is communicated by emitted particles is kind of a way to resolve the mysterious, seemingly magical action at a distance problem. So, why is gravity pulling my glasses downward? Well, because the Earth is emitting little particles called gravitons, and when you get hit by a graviton, that graviton hitting you communicates, whatever, but somehow, right? This idea that, hey, there's, hey, glasses, get on board, the gravity is going that way, so off you go, right? At least there is a contact happening to kind of communicate how the force should be. Right? So this is I'm going to call this a theory in physics, that gravity is actually emitted particles called gravitons. And again, if it were, I'm not saying that it is, all right, this is just a theory. But if gravity were emitted by particles called gravitons, that's what the flow field would look like, and therefore that's what the gravitational field would look like. And sure enough, that's exactly what we observe. So this is, I'll say, at least highly consistent with what we know about gravity. Doesn't mean it's true, but it's not clear how we would prove it false. Okay, anyway. So I think it's a nice way to think about gravity. And again, whether it's true or not is not our problem. For the purposes of Math 219, we can pretend that it's true because everything that we're interested in will work out correctly if it is. So, okay. All right. So that said, I'm going to draw a line right there. We're going to consider here now a different scenario in between these two purple lines. No longer are we going to think about a single point source of mass. Now I'm going to consider some scenario where mass is distributed all over, and we've got a cloud of mass or something. Maybe there's more density of mass over here, less density of mass over here, what have you. And for the moment, don't worry about these constants. Let me just point out that that's the same constant on either side of the equation. Other than those constants that I would like to ignore momentarily, this just says mass is an integral of density, dV. Right? And that's uncontroversial. Of course, that's mass per unit volume times volume, etc. We've seen that a million times. What I have in orange there, is that all right? That makes sense to everybody? Mass is the integral of density. I'm going to multiply both sides by negative 4 pi g. Legal. Maybe a little mysterious, but legal. Right? Okay. So that's our top line. This right here, what's going on there? Roughly the idea here is if you were to ask, you got your solid, you're looking at the boundary of the solid, and you ask how much flux is there of the gravitational field through the boundary of that solid, the very first thing you should ask is, wait a minute, whoa, why are we talking about flux of a force? That's weird. Forces, we've never talked about flux of a force before, right? We've only talked about flux of fluids. And when you're talking about fluids, it makes sense, right? Because if you have a surface and you've got a fluid that's moving through the surface, then you can talk about, then how much per unit time, how much fluid passes through your surface. It's quantity of fluid per unit time. Makes loads of sense in the context of fluid flows. So, weird thing to ask if you're talking about forces, but let me remind you now, we are reinterpreting gravity as being a flow of particles. We are interpreting gravity as a fluid flow. And so flux makes loads of sense now. Right? Flux of the gravitational field, how many gravitons are coming out of this surface? Does that make sense? Before we get into the equation, though, just the idea of, why would we be interested in flux of the gravitational field? Well, we're counting gravitons. Okay. So, all right, so then how many gravitons do come out of our surface? And the answer, all of them. Right? However much mass you got, more mass, creates more gravitons, and they all exit through the boundary, right? Just like when you're talking about light exiting through light bulbs. How many of the photons created by the light bulb exit this boundary? All of them. If it's a 1500 lumen bulb, then you've got 1500 lumens of flux. More bulb, more flux. Well, likewise here. Mass is what creates gravitons. The more mass you got, the more gravitons you're creating. The more gravitons you're creating, the more flux you get. Because that's what flux is. Flux is a measure of how many gravitons are leaving, aka how many gravitons are being created. Does that make sense to everybody? Okay. And so what's the deal with the negative 4 pi g? This is just the constant that you have to throw in to make that actually work. It's kind of a units thing in some sense. Obviously, mass has different units than lumens, right? Or gravitons per unit time, or whatever the units would be here. There's a units issue. And that's all the negative 4 pi g is. And of course, you got to be fair. You got to put it on both sides of the equation. Okay. All right. Okay, so we've made sense out of this. We've made sense, I hope, out of that. Next, we have that equation. That's a freebie. That's just the divergence theorem, right? And so here's the thing. Then this is equal to that, which is equal to that, which is equal to that, and as a result, that integral is equal to that integral. And this is for all solids. How could you have the case? How could the case be that no matter what solid you pick, these integrals are always the same? The only way that could be possible is if the integrands are the same, and that means that we have an interpretation of divergence. So divergence comes from mass density, is the point. Mm-hmm. Does that make sense to everybody? Any questions? Feel free. Okay. All right. And so, yeah, why? You could reasonably ask. Well, divergence. It comes from how many gravitons are being created. That's where divergence comes from, right? If you have some little region and there's gravitons being created in there, that's where divergence comes from. Well, what is it that creates gravitons in the first place? Well, mass density. And so that's sort of the intuitive connection that the more mass density there is, and the more gravitons per unit volume are coming from there, and therefore that's where the divergence comes from. Okay. All right. So nice equations here. And arguably, I mean, these are fairly similar equations, these two equations we have right here. This says flux comes from mass. And now I'm going to phrase this carefully. I'm going to reinterpret divergence to connect to flux coming from mass. Let's think of this as flux density coming from mass density. And if you say it that way, you really see how these are really similar statements. Flux comes from mass. Whether on the whole or per unit volume, flux comes from mass. And choose to view it as a global statement or as a local density statement. Okay. All right. Okay, last thing real quick that we're going to finish today anyway is about electric fields. If you write down the formula for electric fields, then here's the amazing thing. It's also inverse square radial when you have a point electric charge. So, point source. So electric fields structurally are just like gravitational fields. They're inverse square radial, which is just like light bulb photon flow fields, inverse square radial. And so in the same way that I can kind of interpret kind of a light bulb sort of metaphor for gravity, in the same way I can make a kind of a light bulb metaphor sort of interpretation of electric charge and electric fields. And so in the same way that mass shoots out gravitons, or at least we can pretend that it does. Well, likewise, charged particles shoot out a fluid. I don't want to say what the name of the fluid. It'd be confused. It's very weird. Particle physics is weird, and I think it would hurt more than it would help if I said what the names of those particles are. I'm not comfortable with it myself. But anyway, you can pretend that charged particles emit a fluid, and that fluid, the flow of that fluid, is what an electric field is. And then making the exact same reasoning that we did before. Ignore this constant. Quantity is an integral of density dV. We're just adding up charges instead of masses. How much of this fluid passes through the boundary? Well, all of it. Unit conversion constant here. That's just to take care of details. And then you break down the divergence theorem. And as a result, these two integrands have to be the same, and this is one of Maxwell's equations. This is what we call the differential form of what I would call the first of Maxwell's equations. That the divergence of the electric field is proportional to charge density. By the way, this equation right here, also known as Maxwell's first equation. Now, this is uncomfortable at a glance. Wait a minute. These are pretty different looking equations. Why would we call these the same equation? Doesn't that seem inappropriate? Let me say it again with choice of words, carefully chosen. Flux comes from charge. Flux density comes from charge density. They really are the same statement. This is just kind of a global version relating flux and charge. This is a local per unit volume statement relating flux and charge. They say morally the same thing, and just like with gravity, the divergence theorem is the thing that connects these two versions of this equation to each other. Right? So very important to understand the divergence theorem when you're dealing with electric charges. If you haven't had E&M yet, then you're going to have an advantage over your classmates having seen this before. Okay, and we're out of time. So we'll call it a day right there, and y'all have a great break. See you next week. And happy Thanksgiving to everybody.